We are going to discuss lecture 7, where we will be discussing a very important aspect of accelerators, that is beam focusing. And this beam focusing is required for all the experiments. And you can see that the beam extracted from ion source or even accelerated from accelerating tube normally is diverging. For example, if you take the ion source here, there is a plasma here and there is a extraction voltage, then the beam will be going almost like this, because beam is coming from all places. So it will be a very diverging beam. Now this beam has to be focused before it is taken to the target. Otherwise, what will happen if the beam size is big and target is small, then the entire beam will not be used and the results will not be accurate. Therefore, it is absolutely necessary that before taking the beam, accelerated beam to the target, it has to be properly focused. And it will always be preferred if the beam is parallel when it is going to the target. If it is a parallel beam, then it will be preferred. However, this has been done in the case of, for example, light beams. It is done with the glass lenses. And in the case of electrostatic lenses, ion beam which are accelerated, electrostatic lenses or the magnetic lenses are normally used for getting the beam focused. And normally the target size is not more than few millimeters to 1 centimeter, and therefore beam has to be focused to that. Then you will see that both electrostatic and magnetic lenses are used. And in fact, even the dipole magnet, which we always think that dipole magnets are used only for deflecting the beam, if they are given, their pole faces are given the proper shape in order to get the magnetic field components energized, then they also can be used for focusing the beam. But otherwise, normally electrostatic lenses, either electrostatic quadrupole or maybe angel lens, and the magnetic quadrupole lenses are very popular for focusing the beam. Then you will see that if you are using these doublets, that means two quadrupoles, either electrostatic or magnetic, then you will see that one quadrupole always focuses in the one plane and it defocuses in the other plane. And therefore, if you want to have the focusing in both the planes, then you have to use doublet, minimum doublet. Or if you want to have the symmetry of the beam, total rotational symmetry, then it is required to use a triplet rather than the doublet. And these details you will see that these quadrupoles are useful and for both low as well as high energies. However, for very low energies, another simple lens, which is called angel lens, which requires only one voltage, and other two are grounded normally, but it's not necessary that they should be grounded, and they can be used. So there are advantages and disadvantages. If you use magnetic quadrupoles, then you will find that this focusing is mass dependent or the velocity dependent. However, in the case of electrostatic quadrupoles, the magnetic field or the electrostatic field strength does not depend on velocity, and it only depends on the charge, and therefore they are much more convenient to use. However, at low energies, always electrostatic quadrupoles are preferred because they are supposed to be stronger than the magnetic quadrupoles. And of course, the velocity independent, therefore more convenient to use it. At high energies, these electrostatic quadrupoles cannot be used because the voltage which is required to focus these beams has to be of the order of the energy. So suppose you want to focus the some 50 keV beam, then the electrode will require voltage of the order of few keV. And therefore at high energies, the magnetic water poles are preferred, and they are the much better with those limitations of mass dependent, and therefore the current which has to pass to generate the magnetic field has to keep varying with the mass and the velocity. You can see here there is a beautiful analogy between the optical lenses and the electrostatic lenses. You can see here, here you can see the electrostatic quadrupole. All these electrostatic or magnetic quadrupoles, they have four poles. And for example, in electrostatic, it is called positive, positive, and negative, negative. So there are four poles, and these are equipotential lines. So you apply the voltage here. Let's say it is V here, and any voltage, either it can be grounded or it can be more or less. Now, if you see the analogy, then let us take a glass lens which is converging type here, and all the beams, all the particles here at different distances from the optic axis at the distance of d at various d's will be focused here at the same point, because the curvature changes. So the beam which is coming very close to the axis will go almost like parallel, but the beam which is coming very or hitting the lens at larger d's will have much larger deflection angles. So it is that theta depends on the d, the distance from the optical axis to the place where beam is hitting the lens. So you can write, if you write this, then it is almost like you can say the tangent of this theta is equal to d by f. If f is the focal length, which is here to here, this is focal length. And so you can say that, and if the theta is small, then you can write in a simple expression, it is d by f for small d's. So, so if the farther is the particle from the axis, the stronger is the focusing force, and therefore it depends linearly for the small distance d from the optic axis. Now, in electrostatic lenses, there are two types, as I mentioned. One is called angel lens, and other one is called quadrupole lens, electrostatic quadrupole lens. And in quadrupole field configuration, for this one is shown here. You can see that the particle will be focused properly if the opposite poles are of the similar polarity. Now, in the case of electrostatic quadrupoles, which is shown here, that this is plus V here both, and this is minus V. The field, which is a function of an x and y, let's say that this is x, this is y-axis, and this is x-axis, and here the z-axis is normal to this, which is a beam direction. In that case, with following geometry, the field or the voltage distribution, which is a function of x and y, depends on k by 2 into x square minus y square. This, of course, is exact if the geometry of the poles is hyperbola, and then this equation will be used. And of course, I am assuming here that beam is along z-axis. The field errors, of course, has to be minimized, and they depend on the two factors mainly. One is the manufacturing, and that is accuracies, and the other one is the positioning accuracies when you are aligning the things. So if there is an error in the either manufacturing or the positioning of the quadrupole, then there will be errors, and which will disturb the ion trajectories as well as the focusing effects of the quadrupole. These errors not only can change the focusing effects, but also can change the motion of the ions, and they can induce the aberrations which I have mentioned. This is true for both electrostatic as well as magnetic quadrupoles. I have shown here the first one is an angel lens. You can see here this is angel lens, and angel lens has 3 electrodes, and normally 2 electrodes which is at the entrance, at the exit, they are normally grounded, they are part of the beam line, and the center electrode is given the voltage, but it is not necessary that these other 2 should be grounded, they can be isolated also. And if you isolate, then the voltages will be V1 and V1 in the beginning, first electrode, and the V2 at the last electrode, and the central electrode will have this. However, the voltage difference is V minus V1 and V minus V2 in the case of. And you can see the field lines which are responsible for the focusing of this. So basically this angel lens also is a 3 electrode, or they can be 3 cylinders. And these cylinders are applied voltage, and as I mentioned that normally these 2 electrodes, one is at the entrance and the other is at the exit, they are grounded. So if suppose the beam line is coming here, then only central electrode is isolated, and then these 2 are grounded. They are part of the, they become the part of the beam line. So they are grounded, and therefore you don't have to apply voltage. So this V1 and V2 becomes V1 and V2 becomes 0. So V1 is equal to V2 and is equal to 0 means it is grounded. It's a part of the tube or part of the beam line. Only this is applied the voltage V. You can see that how this works. You can see the field lines here, and at any point, for example here, there will be a force in this direction, and this will have 2 components, one in this direction and other one is this, other one is this, and similarly here there are 2 components, and they will be responsible for focusing the beam. You can see here that if one is focusing, the other one will be defocusing, because the field direction will be reversed. And therefore, if first one is focusing or defocusing in this case, then this will be focusing. So it will work like this. But the total focal length will be positive. That means there will be net effect of this lens will be the focusing. Now coming back to, so this is a very simple, but only problem is that this V, the voltage which you have to, even if you V1 is equal to V2 is equal to 0 means they are grounded, you have to apply voltage on central electrode which is V, and that voltage has to be pretty high if you want to go to higher energies, and therefore these lenses are mainly used for lower energies, but they are very accurate, very simple, very cost effective, and they are in general used for low energy accelerators and very effectively focus the beam. However, this is the quadrupole lens, electrostatic lens, and this again, like magnetic lens, which I will explain later, will focus in one plane and defocus in another one. So they always have to be used in doublet and minimum doublet. And if you want cylindrical symmetry then of the beam, then it has to be, you have to have a symmetrical triplet. Now in this case you will see that if first quadrupole is focusing in X plane and defocusing in Y plane, then the second quadrupole, which is rotated by 90 degree, will defocus in X plane and focus in Y plane. So that effective focal length will be positive, and it will be effectively, net effect will be focusing the beam. So this you can see here that as I mentioned earlier, that both electrostatic and magnetic quadrupoles, they have 4 poles. Here, there it was positive, positive, negative, negative. Here it is north, north, south, south. So you can see that if a particle is going, particle in all the calculations, particle direction is always taken as Z, as mentioned. Let's say this is Z, this is the beam axis, Z is always beam axis, and these are called transverse axis. This is called Y axis, and this is X axis, which is perpendicular. So if Y is like this, X is like this, and Z is like this. So these are three axes which you can see, and at any point the magnetic field which is between North Pole and South Pole, so magnetic field will always be like this, and from here to here, and this place to this place here, for example, here. So you can see that if a particle beam is slightly defocused, and if a particle is falling on this point P, then you will find that it will see the magnetic field B, which is perpendicular to this, and it will have two components, By and Bx, which are responsible for focusing and defocusing. So you will see, if you can analyze, which you will see in the next slide, that it focuses in one plane and defocuses in one plane. And for doing that, you will see with the analysis that unless you use the quadrupole doublets, you cannot get the focusing in both the planes. And therefore they are always used, these quadrupoles are always used either as a doublet or as a triplet. You can see I am giving the summary of this, that you saw that this, since the profile of the pole is hyperbolic, let's say, in ideal case, then as we move along this axis, the magnetic field increases, which is By here, this is By and this is Vx, and so as x increases, the distance, this keeps coming down, this distance keep coming down, and therefore the By will keep. So we can always write that By is proportional to x here, and therefore you can write it is equal to G times x. Yes, so G is a constant of proportionality, it's a nothing but a gradient. And similarly, if you go to y-axis side, then also you can write that Bx is proportional to y here as you go, and it is also again like a G into y. This G is proportionality constant here. Now the force on this particle coming here at this point will be written as Fx. You can see here that how this total force is both is E charge times E plus V cross B. And B, I said that B is always along the Z axis. So Vz is really equal to V. Now in this case, when we are focusing with the quadrupole, magnetic quadrupole, E is 0. So this point is 0. This point is 0. So this will not appear. And therefore the force will be force on the particle, which will be responsible for focusing or defocusing, is nothing but charge time B cross C. It's a cross product of velocity and the magnetic field. Now these are all vector quantities, so you can write this force as Ifx plus Jy, Jfy and plus K into Jz, Fz. So these are three components, and the right hand side you can write in the matrix form, and if you expand the matrix form here, then you can write this equation, and from this equation you can write Fx is equal to charge times By Vz. By, this is velocity and this is magnetic field, and as I mentioned that we are assuming that velocity is along the Z axis, so this will be 0, this is 0, this is V, this will be V. So you can write that this is nothing but Vx is equal to minus charge times Vz, Z component, which is, as I said, that if the velocity is in that direction, this will be equal to V, if the V is the velocity, into the Y component of the magnetic field. And you can write similarly equation from this, you can write that it is By is there. Now you can see here, if you compare, Fx is minus this and Fy is plus this. So you can see that in one case, x plane, if it is focusing in x plane, it will defocus in y plane, and if it is focusing in y plane, then it will defocus in plane. And therefore, it is necessary that by proper choosing the parameters, you can focus the beam in both the planes by rotating it, because you have to change the direction, you have to change the sign of that. So, and you have minimum two quadrupoles, one here and one here, and this quadrupole is rotated by 90 degree, so that the field directions will change, and then it will give the focusing in other plane where it was defocusing in the first quadrupole. Now, ultimately, having known this, so this has to be calculated properly. And of course, in the quadrupole, not only you have to use two quadrupoles. If you are using magnetic quadrupoles, they can be close by. Between two quadrupoles, there has to be certain distance. So you have to consider that also. There will be focusing. If the first one is focusing in one plane, then it will keep focusing. There will be a drift tube like of thing. So you have to consider that also. So ultimately, what exactly we want? We want that we want to see how much is the focusing or defocusing, and for that we have to do study the motion of the charged particle both in x and y plane. X and y plane are transverse plane, and this velocity is going in longitudinal. So we have to see the direction or motion of the particles in the field, whether it is electrostatic or magnetic, in both the x and y plane. So let us, and they will be somewhat similar. So you can say that if I study thoroughly the motion of the charged particle in x plane, it will be somewhat similar to that in y plane also. And then it will change when in the other quadrupole, which is 90 degree rotated. So you can write that if you want to study the motion of the particle in x plane, then you will see that the force is Fx, which is responsible, and force is nothing but the derivative of momentum, that is dp by dt, and this is nothing but d by dt of mv, which is the momentum. And therefore you can write this as d by dt within bracket m into dx by dt, because velocity in x plane is dx by dt, and this you can write as m into d square x upon dt square. This is called acceleration. This is nothing but x double dot, derivative of velocity. So if you write all these things and the force coming from this equation here, these equations here, then you will find that our equation becomes like this. This is the equation, you take it to left hand side, then this becomes the equation. So this is the equation which we have to solve in x plane. So this you can, so suppose you write this as, let's say, k, and change the value. See, ultimately you want to know the trajectories as a function of z, because it is the velocity, a particle is moving in z direction. So you don't know time. Of course, you can calculate velocity, but that is not important. So what you want to know, x as a function of z and y as a function of z. These are because that is the transverse planes. So you want to calculate the trajectories of particles in x plane, and which is as a function of z in x and y plane, both of them. So you have to convert, you have to change the variables from t to z here, and you can write that z is nothing but velocity times the difference, and that if you differentiate it, dz is equal to vz into dt, and vz is nothing but velocity. We are taking the particle is moving only in the z direction. So if you write this, then the equation becomes this is the equation which you have to solve, where if you write kx as this e times g upon m vz, then this becomes the equation which you have to solve. And this is a very simple equation which will have a solution where x, which is a function of z, you can see is this is written here. It's a very simple one. And if you differentiate it, then x prime becomes like this. This is the x prime. So these are the two equations you have to solve. First is that how the trajectory is moving as a function of z, and how the divergence is increasing or decreasing. So you have to solve these equations simultaneously, both of them, and see this. Now here you can see that in this equation, there are two constants, a and b, and they have to be found from the boundary conditions and there. So effectively, when we say focusing, it's solution of these two equations and find out that how the trajectory is moving along z. So these are the two equations which have. Now if you do that in a very simple terms, and this 1 by f is given here, and which depends on g, and where L is the length. See, for example, if you have a quadrupole here, let's say you have quadrupole here, normally these quadrupole lenses, magnetic quadrupole lenses, they have a finite distance, let's say finite length here. So this L is a length. While you have seen in the case of optic lenses, glass lenses, they are also having two types of lens. One is thin lens and a thick lens. So in the case of thin lens, you can neglect the thickness. Suppose it is, let's say in the case of converging lens, it is a very thin lens, then you can forget about, you can omit the length. But if they are, suppose this lens was very thick, then you cannot do that. See, similarly, in the case of electrostatic, either electrostatic quadrupole or magnetic quadrupole, this length cannot be avoided if it is not a thin lens. So if L is the thickness of the lens, then you can write the focal length here, which is focal length here, and that is a function of velocity, not velocity, magnetic field, rho, which is a radius of curvature, length or the thickness of the quadrupole, and this g factor which is coming from here. G, you can see that g is coming from here. That's a gradient of the magnetic field. If you put that simply, then you can see here that 1 upon FL is k times this, and these are two, both are constants. And here the k is called the focusing strength. And at this moment, I would like to again tell you that if you have two lenses, it's not that it will give defocusing beam. One is focusing and other one is defocusing. So suppose you have a combination of two lenses, then if a net effect will be focusing. So suppose either you have focusing and defocusing, or you have defocusing earlier, and the defocusing here like this, and the focusing later on, still the effect will be, and that you can put, still it will be focusing effect only, and therefore if the beam is coming here at let's say 2 centimeter, I'm just putting it, then you will get the beam here focused at certain distance, and it will be much smaller. It will cross at this. So there will be some focal length, and that focal length will be equal to FC, which is called combined focal length, and that is equal to 1 by F1. F1 is a focal length of the first lens, plus the 1 by F2. F2 is a focal length of second lens, minus the D, and D is the distance between these two. D is the distance gap between two lenses. So if you put that, you can put any one of them, either F1 you can put negative, that means defocusing, or you can put positive, and the other one other way around. If you put either of them, you will find that it is always the combined effect. The combined effect is always positive, and therefore any combination of lenses, either focusing lenses, or converging or converging diverging, or diverging focusing, or any combinations you have, this FC, combined focal length, will always be positive, and therefore the net effect of this will be net effect will be focusing. So this is just to give you an idea, and here I have given some idea about the how the mathematics works, and how the trajectories can be calculated, and similarly you can do in y plane also. And if you do this whole thing, the trajectory calculation, and see that how the focal lengths in x plane and y plane looks like, then you see that these focal lengths are given here, x plane and y plane both, and you have a focal length here, and the trajectory will be, when you want to calculate the trajectory, then you have to inject a parallel beam here, and then see that at what point they will be. Of course, there can be aberration if the proper machining of these lenses is not done. Here it is deflection. So here you can see the parallel beam coming here is focusing at this plane, and here in this case it is diverging. It's a diverging lens. So the trajectory is going like this. So it will be crossing the optical axis at a point opposite to that. So this becomes like minus f. So this is direction. So that is why I said that. And normally in the case, if you want to have a good quality beam image, then this focusing and defocusing focal lengths in magnitude are equal. They are kept equal. The design is done in such a way that they are equal, and these are almost identical, and therefore you can get a idea of in any experiment. Idea is that you should have a smallest beam possible, and as far as possible it should be very close to the circular beam, and that you can have circular beam if the instead of doublet, if you use triplet and analyze the whole thing in the same manner using the same philosophy which I explained just now, then you will find that with triplet you can get a very symmetrical beam, rotational symmetry you will get it, and the aberrations will be very small.